Hello, everyone. I'm Zhang from New York University. Thanks for attending our presentation. In this talk, I want to share with you the challenges, opportunities, and thoughts on managing the fluctuating workloads in machine learning as a service system. This work is collaborated between NYU and Microsoft. Deep learning, or in general, machine learning, is everywhere and has changed our daily life. With the help of modern high-performance hardware, such as GPUs, deep learning has been able to surpass human performance in many application domains, such as computer vision, natural language processing, self-driving, gaming, and even arts. The state-of-the-art DNN consists of many layers of computations. Take the image classification, for example. It uses multiple convolution layers to extract the low-level through high-level features from an input image, and at the end, several fully connected layers are applied as a classifier. Notably, convolutional operations account for more than 90% of the computation in convolution neural networks, and it dominates both the runtime and energy consumption. Computationally, at one convolution layer, it convolves each filter over the input image and produces a 2D output. When we stack multiple 2D outputs from different filters together, we get the 3D output tensor as the final output for this layer. And this output will be processed by the following layers until finish. From this process, we can say that the execution time of DNN really depends on the neural network steps and also the activation and the filter size in each layer. To build up a machine learning system, multiple processing stages are involved. The typical life cycle starts with the model development. It involves the data extract, transform, and the load process. It also builds the future function, designs new model architectures, tune training algorithms, and validates the prediction accuracy. With the recipe from the model development on how to train the model, data engineers can then retrain the machine learning model at scale on live data and managing the model versioning offline. Once the model is well trained, it can be deployed for inference serving. The smaller machine learning model can be deployed in power-constrained mobile and IoT devices, while for very large DNN model, due to the computational expensive nature, inference is increasingly outsourced to clouds to render predictions as a service. As of today, several companies have enabled machine learning as a service in their cloud computing platforms, which include Microsoft, Google, Amazon, etc. There is also prototype effort in academia, such as Clipper from Berkeley. Although substantial efforts have been invested into the development of machine learning as a service with the goal of the high throughput, low latency, and high elasticity, one of the main challenges is how to deal with dynamic workloads. Existing solutions have several limitations. For one, in classical machine learning development lifecycle, new models are developed offline and versioned statically. That is, each application is tied to only one specific model at runtime. Secondly, in the event of load spikes, current approach chooses to prune certain requests according to some matrix. However, this results in QoS validation and will make the customer unhappy. Alternatively, they would add significant new capacities through auto-scaling technique. However, this is not economically viable, and the provider will not be happy. Most importantly, these design choices make it really hard to sustain QoS when workloads fluctuate. For example, recent news reported that during coronavirus, Microsoft cloud use spikes more than 700%. The impact of this includes the service success rate dropped below 99.99%, and the team software suffered a 2-hour outage in Europe. The solution that Microsoft currently takes is try to limit the new service. That is essentially to prune the request. And they also plan to scale up hardware resources. In this work, we try to address this challenge in a slightly different way. Our approach starts with the opportunity that DNN models themselves can offer. We observe that for the same application, we can train many different models of varying computation complexity and accuracy trade-offs. For example, we profiled the single image inference time for multiple pre-trained ResNet models given different amount of computing resources or threads. By the way, ResNets are those very deep convolution neural networks which contain residual blocks with identity function as their element. Back to the plot, we can observe a more than 5x spread in execution time. Complex, deeper models are also more accurate, shown here. All these observations provide us a large design space to explore when designing machine learning as a service system. In the machine learning as a service system, two sides are under consideration: end user and service provider. The provider renders the predictions for the request sent from the end user. There are usually certain service level agreements made between them to guarantee the quality of service, such as latency, throughput, and cost. We also assume in this work that we would see fluctuating workloads, and we only have a fixed hardware capacity. As we saw in the previous slide, for machine learning applications, the service provider will have the opportunities to choose A, which model to use, B, how to allocate hardware resources. All these decisions will be made online and should meet the user's QoS needs. So now the question is, what should be considered as QoS for such machine learning applications? Well, the answer depends on what the users care about. In general, user wants quick and correct predictions. Imagine a user send an image of cat to classify. Now the cares about A, latency. A prediction that past due would degrade the quality of service. B, accuracy. Even if the latency is guaranteed, the incorrect response is not expected. Note that while these two scenarios may seem to be very different, they are interchangeable. Instead of incurring a deadline miss, a user could simply randomly guess the answer within the deadline at the expense of accuracy. Therefore, we believe in machine learning as a service system. Users are interested not only in the fraction of predictions returned within a deadline, but more importantly, the fraction of correct predictions within the deadline. In other words, prediction accuracy within the deadline should also be a critical quality of service metric for machine learning as a service system. But the question now is how to specify this in the service level agreement. This motivates our new metric design, effective accuracy. It targets users' needs for both accuracy and latency. Mathematically, effective accuracy can be specified as the product of the machine learning model's baseline accuracy and its deadline meet rate. We observe that empirically at low load, when the most complex ResNet model always meets the deadline, it can provide the highest accuracy, effective accuracy. However, as load ramping up, simpler models have higher effective accuracy than more complex models, because the large model now incurs a much higher fraction of deadline misses. Given this, the service provider can potentially swap out complex models for more computationally efficient models while preserving effective accuracy at high load. This flexibility is enabled by looking at effective accuracy, and it gives us a Pareto optimal when dealing with workload spikes. Also, for service provider, as a request queue up for processing, two decisions can be made to exploit the parallelism and different granularity. A, how many requests can be served in parallel? This answer depends on the number of backend replicas in the system. B, once a request is assigned to one of the replicas, how many threads should be allocated? To study this, we assume a fixed capacity, but varying the replica and the threads configs at each node level and measure the end-to-end latency in the client side. It can be observed that carefully picking the replica and the thread configuration is necessary. And from the plot, it shows that as the load increases, adding more replicas seems more favorable than threads. Based on observations so far, we can build our online model switching framework. Our framework monitors and predicts job arrival rate and switches between the models to maximize the effective accuracy. More specifically, it first, for each SLA deadline, we train a policy offline that gives us the best model and the parallelism strategy at each load level. At runtime, we monitor the request arrival load and use the load measured in a given window as a predictor for the next window. The model switching controller then searches and picks the model and also the replica and the thread configuration that has the highest effective accuracy based on the load. We build our model switching controller into Clipper, an open source online prediction serving system. To be focused on this study, we disabled the caching and the dynamic batch size adaptation in Clipper. The sample period of our controller is set to be 1 second. We have two separate virtual machines for model serving and querying. We set the batch size of 1 when posting the request. We use pre-trained ResNet models in PyTorch and deploy them into container in the Clipper. We also implemented a Markov-based model-based load generator to emulate user behavior. The plot shows the load profile over a 300-second window and the models selected by the model switching controller during the period. From the figure, we can say that the controller selects most accurate but also computationally expensive ResNet 152 model when the load is relatively low. For moderate loads, the controller switches between ResNet 101 and ResNet 152 models. However, when the load spikes at around 152-second mark, the controller can quickly adapt and switch to the smaller models. Note that all the switching happens in real time together with the prediction serving. The results here account for all the overheads, such as switching between models. Here is the effective accuracy of the proposed model switching controller compared to the baselines that only use one single model for serving the same trace. We observe that since both ResNet 18 and 34 are fast and never miss deadlines, their effective accuracies are simply equal to their baseline accuracies. The effective accuracy of the larger ResNet 50, 101, and 150 models reduces as the deadline constraints become tighter due to the increasing deadline miss rates. In contrast, model switching yields the highest effective accuracy for all deadline constraints. We note that this effective accuracy would be unachievable by the smaller models and only achievable from the larger models by introducing additional hardware resources otherwise. But in our work, we are not going to scale up the hardware resources. To better understand how our model switching adapts to the load fluctuations, we plot the empirical CDF of the end-to-end latency observed by the client. For smaller models such as ResNet 18 and 34, it guaranteed that 100% of the queries can finish within the deadline, but have low baseline accuracy. Large and more accurate models suffer long tail latency and would result in severe deadline misses. Model switching, as it stands, seeks to combine the best of both worlds, that is, meeting the deadline on the one hand, while serving requests using the most accurate model whenever possible. That's all of our talk. We thank your time for watching this and welcome the questions for discussion. Thank you.